Looks like we're live. Hello everyone and welcome to another Zozin session. How about that? Bet you didn't expect that shit to happen. Right, let's make a little bit of an announcement and post a message in our Discord server. So this is going to be a red circle live on Twitch. Hello everyone. Hello Duke, Zaylin Zero. Hello, welcome. So what are we doing today? Today we are developing actual compiler. That's what we're doing today. You know, the same thing we do every stream, pretty much. And the topic of today's compiler development is going to be refactoring of the memory management. That's right. So for those who doesn't know, what we're doing in here is we are developing a compiled programming language called Porth. You can find the source code to this language in the description, and if you're watching live, you can find this thing in the chat, right? Just issue a project command or today command. So, and this is a stack-oriented concatenative language. And this is actually wrong ribbon, so it's actually on GitLab. We recently moved to GitLab because GitHub buttons are kind of meh, so we had to move there. So, and yeah, we had one way to work with a static memory, and to be fair, it's a pretty crappy way. I introduced that way as like a quick hack, just to have something in terms of memory for the language. And now as we develop more and more complex things, including the compiler itself, right, we're rewriting the compiler in itself, we're starting to have a little bit of a problem with managing static memories. So I think the time has come to finally refactor and a little bit like redesign the way we allocate and manage static memory. So, and that's going to be the topic of today's stream. So to refactor and redesign the way we manage the memory, we need to sort of recap how do we manage the memory right now. So and what's so bad about that way of managing the memory. All right, so let's go to the repo and consider a couple of examples, I suppose. Hello everyone. Hello Parademi, Manasoimia, Loop 327, Fusery, Udliniueli. I hope I'm pronouncing them correctly. Hello. Membrilla Amarilla, hello, welcome. So let's take a look at some example. Let's create test.porth, right? And let's include the standard library, so std.porth. It's a very simple language. You can basically sum up two numbers and you can then print them. So let's try to compile this entire thing. So this is going to be test.porth, and so yeah, we need to save this entire thing. Membrilla Amarilla resabbed with thank you so much for 9 months of Twitch Prime subscription. Thank you, and welcome to our epic Porth club. That's right, Porth. So we compiled this entire program, and the compiler produced an actual executable that you can then just run. So the executable will sum up 34 and 35 and print the result. And if I run this entire thing like so, as you can see, it printed 69. So it's a stack based. So essentially it used stack to store all of these operands of the plus operation. But using only stack is not really sufficient, right? So we also have some sort of like a reserve chunk of memory, right? In fact, if we take a look at the compiler itself, so there is a constant here called mem capacity that is equal to 640 kilobytes, because 640 kilobytes should be enough for everyone, right? So, and if we take a look at how we use this constant throughout the compiler, we'll see that we just allocate a chunk, a static chunk of memory, of the size of 640 kilobytes. And that's essentially the whole static memory that you can have. Right. So again, this is a pretty crappy way of managing the memory, but I introduced it as a quick hack just to have something. And the way you access that memory is just like you use a word mem, which pushes the pointer to the beginning of the memory onto the stack. So then you can read from that memory, or you can write something into that memory. Right. So, and essentially, If you want to, for instance, save two 64-bit numbers into the memory, you have to do it like that. You put 69 onto the stack, you put a pointer to the beginning of the memory, and then you write that value at that specific place in the memory. So if you want to put a next number like nearby, what you have to do, you have to put that number onto the stack, and you have to take the pointer to the beginning and offset it by 8 bytes. So you basically have to manually offset that memory and manually maintain the layout of the memory. Right, there we go. So essentially, I just basically reserved 16 bytes since the beginning of the memory, and in the first 8 bytes I put 69, and in the second 8 bytes I put 420. So, and that's how you manage the memory throughout like the entire language, right? So again, it's pretty crappy, but the language is still in the design process, right? It is what it is. And for instance, if you want something more convenient, right, let's say you want to have specific names for these regions of memory, well, you can use macros, right? So you can create a macro called A, and you say that A is basically located at the beginning of the memory, right? So this is where it's located. Then if you want to have B that is after A, you say it's located after A, 8 bytes to the right. And there you go. So after that, you can just say A, and here you can say B, because the macro will basically expand into the sequence of these tokens, and A will expand into mem, right? So essentially, you not only managing everything like manually, but you also have a mechanism of tucking all of these like layout operations like behind the macros, so it looks a little bit nicer. But under the hood, it still expands to a lot of like different calculations trying to find the location of the memory, right? And after that, you can do something like A, read that value from the memory, then B, read that value from the memory. You can sum it up, and then you can print this entire thing, right? So, and let's recompile the entire stuff, and let's run it. And as you can see, there we go. So it works. We saved two numbers into the memory, then we read them from a memory, and then we summed it up and printed it. So this is not particularly convenient way to work with the memory, as you get more and more different variables that you need, right? So as already mentioned, we started to rewrite the compiler in itself. Right, so we have a file in the source code called porth.porth. Right, so it's a rewrite of the compiler in itself, and we have a lot of variables in here, right? So not that many yet, but we're gonna have more. So as you can see, all of these things are essentially variables, right? So, and they are allocated the way I just explained, right? So basically we chain them together. So the first variable, put D buffer, it starts at the beginning of the memory. So then here's the next variable, here's the next variable, here's the next variable, here's the next variable. They have different sizes and they actually depend on each other. So you see content comes after stat buffer, and the size of stat buffer is that, but stat buffer comes after FD, and FD comes after that, and so on and so forth. And if you want to add a new variable somewhere in between, you have to make sure that you chain them properly, right? You see, it's kind of like doable, but it's kind of crap at the same time, right? So, and on top of that, you have a limited amount of memory, yet again, 640 kilobytes. And recently, I already hit the limit of these 640 kilobytes. Really, like I wrote a program for which it is not enough to have 640 kilobytes. So Bill Gates was actually wrong. 640 kilobytes is not like enough for everyone. It was not enough for me. And one of the programs that I wrote that exceeded that limit is one of the Project Euler solutions, right? So I solved a problem 10, I think. So this is a problem 10. And essentially, the problem 10 was about summing up, finding a sum of all of the prime numbers below 2 million. Right. So, and I used 64-bit numbers to represent, to store those prime numbers. And all of them didn't fit into 640 kilobytes, so I had to implement 32-bit intrinsics to compress this stuff a little bit. So I had to actually use 32-bit numbers instead of 64 because I had a limit on the static memory. So obviously we have a lot of problems. This kind of approach was okay for a while, but we're starting to hit the limit on that approach. And furthermore, this approach does not allow us, for example, to let the standard library reserve a little bit of a static memory for its own usage. Right. So essentially, here is the root program. Root programs divides the whole chunk of memory, the whole 640 kilobytes starting from the mem. But what if the standard library wants to get the chunk of that memory? How the standard library tells the user program that, okay, you can I reserve this amount of memory and you can allocate the rest starting from here. I guess it can introduce another macro, right? But what if you have several libraries that all wants to allocate a little bit of the memory themselves in the static memory, right? So how do they communicate with each other? How the different parts of the program will communicate what kind of parts of the memory they allocate? So it doesn't work out that easily. So again, this approach is okay for small programs, but as you start to develop more and more complex things, you need something better, right? So the simplest thing that I could think of is to introduce another construction that lets you sort of reserve a chunk of memory of a particular size and give that chunk of memory a name. So essentially, let's take a look. So this is going to be test Porth. So instead of writing like this, right? So let's actually completely ditch the mem, right? And let's introduce a keyword, something like memory, right? So we don't even have a highlight for that keyword, but let's actually go to the editor support and change. Let's just add another keyword in here. So here are all of the keywords of Porth, and let's introduce the keyword memory. I'm gonna reevaluate the entire thing and I'm gonna revert this buffer. There we go. So now we have a new keyword called memory. So, and I'm gonna say allocate 8 bytes, right? And then allocate 8 bytes for B, and that's it. So, and this will essentially allocate 16 bytes, and you can just refer to these chunks of memory by their names. I think that will be actually super convenient, and again, that will solve all of the problems that I'm talking about, right? So you don't have to manually maintain the memory, right? So you don't have to chain things together. You just say, okay, here is the how much memory I want. Please assign a name for this entire thing. Right. It also lets the standard library to reserve a chunk of memory for its internal usage, and it also gets rid of the limitations on 640 kilobytes, because you can allocate as much as you want. You can in fact allocate 1 megabyte, right? So and what's interesting is that implementing this thing is relatively easy, right, if you just accept a number. But quite often, and here's an interesting thing, the size of the allocated memory is computed as a mathematical expression from other constants, right? For instance, I want to allocate an array of 64-bit numbers, right? So, and imagine that I have a macro size of U64, which is just like U8, and then I say, okay, and I also have a macro like n, which says that I have 69 of these numbers. And based on these two constants, I want to do what, right? I want to allocate size of U64 n times. Right, so that means we need to have mathematical expressions in the sizes of the memory. But since it's a static memory, these expressions has to be computed at compile time. Right, so we just wanted to, allocate a little bit of a static memory, but now we're going into a pretty deep rabbit hole of a compile time evaluation. Right, so, okay, so, but do we really want to refactor our entire compiler to support the compile time evaluation just to be able to compute the size of the memory? I'm just trying to rewrite the compiler in itself, if you know what I'm talking about, and I just don't want to overcomplicate it. And I was thinking about this problem, like, yeah, I want to have this feature. I want to be able to reserve a specific amount of memory, right? But at the same time, I also need to be able to compute the sizes of these chunks of the memory based on other constants, which requires compile time evaluation, but I don't want to go into compile time evaluation because it will overcomplicate the compiler. So what do I do? All right. So, and in fact, I was thinking about this problem like for more than a week. Like, what the hell do I do? And I came to a compromise. So essentially, I'm going to implement compile time evaluation. But it's going to be a limited compile time evaluation. So essentially, the compile time evaluation within the memory block for the size of the block is going to be limited to numbers, plus operation, and multiplication. Anything else, if you try to do anything else within this block, it will be a compiler error. Right, so it will be compiler error. And what's interesting is that since these three operations, push a number, plus, and multiplication, are so simple, we can do that compile time evaluation at the parsing. So we're going to evaluate those expressions at the parsing, which will eliminate the need to refactor and re-architect the whole compiler. Right, and then once we're done with the rewriting compiler in itself, maybe at some point we're gonna like implement a proper compile time evaluation. But just being able to use numbers, multiplication, and addition inside of this thing is gonna be enough for now. Right, we don't have to implement everything at once. We just need to implement enough functionality to re-implement it itself. So that's gonna be the topic of today's stream. So we need to implement this construction and get rid finally of the mem thingy, right? Does anyone have any questions so far? You don't actually need to do that. Just use a bump allocator and evaluate it at runtime. Just use a bump allocator. So, okay, so bump allocator allocated a little bit of memory and gave me the pointer to that memory. Where do I store the pointer to that memory? Where do I store it? I can store it on the stack. But what if I have a lot of pointers, you know, to allocated memory? So, and I need to store them somewhere. So where do I store them? I guess in the memory, in some sort of a static memory, which I still need to allocate statically. So we kind of went full circle in here, you see? Anyway, so does anyone have any other questions? What if you had compile time macros so that memory intrinsics only accept compile time constants or macros that are computed at compile time? Sure, that will overcomplicate the compiler and I need to rewrite the compiler in itself. And I don't want to overcomplicate the compiler. I already mentioned that. So I cannot input a not defined number of numbers because it's runtime. I'm not sure if I understand the question. Okay, so don't see any questions, so let's go ahead and implement this functionality. All right, so to implement this functionality, I think I want to have some sort of example, right? I was thinking about, so also these kind of chunks of memory are going to be extremely useful for local variables, right? For some sort of local variables. One of the operations that I really needed while doing some stuff is actually Mem Copy. Right, and I want to implement Mem Copy the following way. So this is going to be macro, and we're going to accept the size of the chunk of the memory that we want to copy, right? Then we're going to get the source, and then we're going to get the destination, right? And it will essentially just save this thing into the destination. The reason why I use this kind of order of the arguments, right? So let's actually put it like that, is because the strings, right? they push first the size of the string and then the pointer to the beginning of the string, which will make me like super easy to just do something like this, right? So I push this thing, the first argument is going to be size, then the source, and here is destination, and I can just like mem copy the string literal into this place, right? So this order of the arguments are going to be like very useful, right? So, and as you can see, we have 3 arguments in here, and manipulating three arguments on the stack is kind of tedious. It's been demonstrated multiple times throughout the Porth development that if you have more than 2 input arguments, it's actually quite difficult to you know, juggle through them. So I want to save them into some sort of intermediate memory, right? So since we don't really have procedures and like a local variables and stuff like that, for now we can just do something like memory and mem copy size, right? So when the size is going to be 8 bytes. So then mem copy src and mem copy dst. Right, there we go. And so essentially we only gonna use these 3 chunks of memory for that specific macro, right? For that specific macro. So, and before I can go ahead and just process this entire thing, I'm gonna just simply do mem copy dst, and I'm going to just save the current dst into here, right? Then I want to save mem copy src 64, and then I want to save mem copy size, right? 64, and there we go. So I have all of the 3 arguments into the macro into these like 3 intermediate variables, and now it's relatively easy to organize the loop, right? So we're starting from 0, and while mem copy, oh my god, Emacs, what are you doing? Size, read this memory while it's less, we're gonna go ahead and just increment this entire thing, right? There we go. So, and in here, we duplicate the index, all right? Then we push mem copy source, we read whatever we have in there. By reading it, we're actually reading integers, so we have to cast it into the pointer, and then we reading the 1 single character, right? So now we have something like, I would say, index and the source character on the stack. So the next thing we want to do, we want to copy index over, like so. Then I want to do mem copy dst, so mem copy dst, which I need to read, like so, and I probably also need to cast that entire thing in here. So to be fair, I forgot a very important thing. I forgot to actually add the indices, like so. Right, so, and only then dereference this entire stuff. So somewhere here we're gonna have something like this, and there we go, we're just saving it like so. Right, and there we go. So essentially we are iterating through the memory and we're just copying byte by byte, right? Of course it is slow, and something like mem copy has to be implemented with, you know, with the most efficient of sequence of operations for the platform, and maybe it should be intrinsic. But for now, since we're not going for the performance, we're just going for something that works. I think this is going to be fine. So, right, and after that I can just drop the index. So what I want to have, I want to be able to define something like this. Does it make sense? Shouldn't be plus be after deref. I think you're right. Yeah, I think plus has to be after the dereference, like so. Yeah, because first we need to read the pointer that we store in there and then offset it. Okay, that makes sense. Okay, thank you so much. All right. So, and what we're gonna do in here, so let's actually allocate some sort of like memory, hello, and let's say that specific memory is gonna be 256, right? And what I want to do in here is I want to take the string literal hello world, right, and I want to save that thing in here, right? That's what I want to do. So, and since this is going to be the static memory, it's going to be allocated in a BSS section, right? So it will be automatically ended with 0. So it's automatically C string. So after that, I take the hello, I convert C string to like a regular string and I'm trying to print it. So there we go. So this entire code will be sort of confirmation that we successfully implemented this memory model, right? All right, so right now this entire thing doesn't work, but hopefully we can make it work. Okay. So here's the Porth. So I think I forgot to save something in here. I'm not sure. All right. So how are we going to be implementing all of that? We're going to be implementing the usual way you implement any compiler feature. You try to compile your program, right? So we're going to try to compile this entire thing, test Porth. And as you can see, it says unknown word memory because the feature that I just described does not exist. Right, everything I just said about this memory feature, it simply does not exist. This is a fictional program, right? It's a program written in a non-existent language. I just made it up. But our goal within today's stream is to actually make it true. Right, we're going to be trying to compile this program and change the compiler until this entire thing compiles. And once it compiles, we implemented the feature. You see, it's that easy. Right, so this is how you develop compilers. People always ask, how do I start develop compiling? How do I start developing an interpreter? Just make up a program in imaginary language. Try to compile it and change the compiler until it can compile your program. And that's how you develop the language. It's that easy. Seriously, I do that all the time and it works. It's a secret that nobody's going to tell you. Everyone is going to tell you, just read a Dragon book or crafting interpreters, but in reality, you just make up the program, try to compile it, and change the compiler until it can compile it. That's it. That's the entire thing. Just make the thing compile, exactly. Chat, you got it. Alrighty. So first, we don't have the memory, right? As far as I know, the memory is supposed to be a keyword, right? So let's go to Porth and introduce that keyword. So we have a class key, there we go. So here are the keywords. Let's go ahead and introduce the memory keyword, like so. And see what's going to happen. So once we introduce this keyword, some of the assertions failed, right? So we don't have an exhaustive handling of the keyword names. If you introduce the new keyword, you have to introduce its name, right? So we're going to have a memory, and here we go. Here is the memory. Cool. So, and I forgot to update this thing. So where is the other place it's going to fail? Okay, so we are failing at parse program for tokens. Okay, so now we need to update our parsing. So here are different keywords. We're handling keyword if, elif, else, and, while, do, include. I'm interested in macro. Here is the macro, because this entire thing is going to be kind of similar to a macro, if you know what I'm talking about. Right, so we have elif token value equal keyword memory, right? So Emacs, what are you doing? What are you doing, Emacs? Emacs, not implemented. There we go. So this is going to be not implemented. So I think here I'm going to go and increment it by now. And there we go. We're failing in here. So essentially, I want to do the same thing as I do with the macro. I want to take a look at the first argument, at the first token after the memory keyword. And if it does not exist, I want to say expected memory name, but found nothing, right? And for instance, if I do something like, I don't know. So to actually trigger this kind of problem, you have to comment out like everything in here. I think that's what you have to do, right? So you have memory, and then here is the end of the token stream. So, and that will trigger that error. Yeah, expected memory name, but found nothing, right? So that's how we basically do that. Okay, so, but if you have something, we have to check that this thing is a word and not anything else. So let's go ahead and just do that. So you see, also implementing a feature in the compiler is just basically copy-pasting code from other parts of the compiler, right? So memory is almost like a macro, so I'm copy-pasting code from a macro, and that's basically it. So see, developing a compiler is easy. It's easy. Okay. So expected memory name to be that thing, but it was something else. So essentially you will have a problem if you try to do something like this, right? So you have memory 8, 8, and this should not compile. This should tell you that you did a fucky wacky, right? Expected memory name to be a word, but found a keyword. That's very strange. This is not a keyword. Huh. This is already kind of strange. This is already kind of sus. Not gonna lie. And this is because I forgot to pop the token. That's right. So I forgot to pop the token. So now it should say memory name to be a word, but found in integer. Okay, so, and of course it should not be an integer. So this entire thing has to be, you know, memory capacity size. There we go. And now we actually passed all of this stuff, and we are at not implemented yet again. So after you implement memory, would the mem intrinsic be implemented with it? For backward compatibility, yes, right. So because I already have a lot of like code that depends on this mem, and while I don't get rid of it, I'm gonna just define memory. So Porth 640 like this mem, and after I'm done with all of that, I'm gonna remove this entire thing. In fact, in the standard library, I have a section which is called deprecated words. Here you will find all of the like deprecated words that I use throughout the development of the compiler. So if I rename something, if I change something, I usually like drop a replacement for this thing in here, just in case there is some code out there that uses those like deprecated words. And what I'm gonna do, I'm gonna just like do it like this, right? So it's gonna be one of the deprecated words. And after we're gonna have like official release of the compiler, I'm gonna just like at some point remove all of the deprecated words, right? So that's basically what I plan to do. So if you're using the mem intrinsic, your code is still going to work. It's just going to use like a different feature. That's basically the plan. Deleting legacy, exactly. This one is really funny, right? So we implemented logical not. And logical not is basically casting a boolean to integer, subtracting it from 1 and casting it back to the boolean. Because not is bitwise not, right? And if you take 1 and do bitwise not on 1, you won't get a 0, right? You would get, I guess, -1, right? Or something like that. So I had to do this kind of thing. Right. Yeah, maybe we'll have to do something about this at some point. -2, yeah, because it's a 2's complement, and you will have to add 1 to get -1, right? So there is an error in your README. The right intrinsics claim the location should be the first instead of last. Okay. Let me see. Memory. Yeah, I suppose it is kind of an error. Right, it is correct for this one, but it is not correct for that one. Okay, thank you so much. Thank you so much for telling me. So this is what happens when you copy paste, right? Don't copy paste, kids. It is dangerous. It is a very dangerous thing to do. Okay, so thank you so much. All right. So what I was doing. All right, so we are about to evaluate the expression, right? We're about to evaluate the expression. So I suppose one of the things we want to do, we want to also check if the memory was already defined and stuff like that, because that's what, you know, those things are doing, right? So for example, macro checks if there's already defined macros, and also checks if there's already defined intrinsics and stuff like that. I think they also should check if you're trying to define a keyword, but I don't think it's going to be a problem because keyword is a different kind of token, so it will fail already here, so it doesn't need to be like that. So it doesn't even need to be like that. Erhan Kurnas, I hope I pronounced your name correctly. Thank you. Thank you so much for 10 months of tier 1 subscription. Thank you, thank you, thank you. And welcome to our epic Porth club. That's right. So we need to keep track of what kind of memory we allocated, right? So let me see. So we already have like a dictionary for the macros. So maybe we could introduce something like memories, dict, and essentially I think what we can do is just map a particular name, right? So we can map a particular name to a particular memory address. I do think we have a memory address thingy. Do we? Do we not? I don't think so. Okay, so maybe we'll have to introduce this thing. Right, mem address. No, we don't have that, but we probably have Mkalo. Thank you so much for tier 1 subscription. Thank you, thank you, thank you, and welcome to our epic Porth club. All right, so we do have OP address, right? So we have OP address, and I think I'm going to define this thing like so. So this one is going to be a memory address, right? So let's go back. So memories. Sounds funny. Now, not implemented. So can you redefine the already existing macros? I think you should be able to have the same name as macros, because you may want to. It's actually really hard. Like, I don't know. Maybe I shouldn't care about that. So it's probably fine. All right. So if the token value, right? If token value is located in memories, right? If it is located in the memories, we have to report an error saying that you're trying to redefine the existing memories. So I'm going to actually make it a to-do, right? Because I don't want to think about the reporting, right? So I'm going to implement that a little bit later. So to do redefinition of a memory, right? Of a memory region, rather, right? So this is the redefinition of a memory region. Okay. After that, we probably want to check for intrinsics, right? We want to check for intrinsics. So if the token value is in intrinsics, this one is going to be something like this. To do redefinition of an intrinsic, right? Of an intrinsic. And should we care about a redefinition of a macro? If you're trying to create a memory region with the same name as a macro, does that make any sense? I'm not sure, to be fair. Right. It only makes sense if the macro has only one token, but if it has two tokens, it doesn't really make much sense anymore, you see? So maybe I'm gonna go ahead and just say, if you're trying to redefine a macro, right, so if the value name is located in macros, you're doing something weird, right? So maybe we're gonna call this memory name. This is a token value, right? And memory name. So another one, a memory name. Memory name. There we go. So redefinition of an intrinsic, a redefinition of a macro, right? Of a macro. All right. So, and in here, maybe if a macro tries to redefine a memory, we also should throw some sort of error, right? So if token value is in memories, right? If it is in memories, we're going to do assert false to do redefinition of a memory. Right, so there we go, We checked all of these things in here. Okay, So if I try to run the entire thing, right, so it still says not implemented. It still says not implemented. Now we want to start the evaluation of this entire thing, right? Now we can start the evaluation. So people saying that lines wrap too much. We can actually toggle truncate lines, and now looks like this. Is it better? Now I can make it as big as I want, and the lines are not wrapping anymore. Is it more readable for you guys? I can try to keep it like that. So, though I cannot read what's going on in here, which is kind of annoying, so I have to like toggle it back. I'll have to toggle it back, I'm really sorry. Okay, so now what I need to do, I just need to start iterating the tokens, right? So I need to start iterating the tokens. So while we have some tokens in here, right, while we have some tokens in here, I'm gonna actually pop that token, right, like so. And if the token type is equal to the keyword, right, so we're already basically going through whatever tokens we have in here, right, so maybe 2, 2, 2, 2, plus, 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 right, so we're going through all of these tokens and we're going to be evaluating it in place, right. We're going to be evaluating all of that in place. Where is my porth.py? There we go. So if we encounter a keyword, that keyword better be AND, right? If token value is equal to keyword AND, we'll have to break the loop, right? We'll have to break this entire loop. Otherwise, if we encounter something else, we have to probably report an error. To do unsupported keyword in memory definition, right? Okay, so if we encounter, for instance, an integer, so if a token type is an integer, token type integer, token type integer, what we have to do, we have to basically push that token onto the stack. But where are we going to have this stack? So we're going to just allocate a temporary stack, which is going to be a list of integers, like an empty list of integers, right? Right, so we're pushing this entire thing onto the stack, and that is basically it. If we encounter token word, right, it might be one of the intrinsics, right? So token word. So what kind of intrinsics we expect? If token value equal intrinsic name, right? Intrinsic plus, right? If we encounter intrinsic plus, what we have to do stack pop, right? Then we have to like pop two values out of it, and then we have to push back a plus b. There we go. So if we encounter some other intrinsic, for example, multiplication, we have to do pretty much the same thing. But multiply. Otherwise, we're gonna say that we have encountered unsupported word. Though, if we encounter an unsupported word, maybe we want to be able to expand that word from a macro. But let's actually think about that a little bit later, right? So this is gonna be false for now. I'm gonna just say to do unsupported simulation within compilation. It's more of a simulation within parsing, right? So the subset of Porth that we're simulating within the memory definition, right? The subset of Porth in here is so small that we can simulate it during parsing, because why not? Right, so we're not trying to simulate like syscalls or something else, right? Access into the memory. No, we are simulating integers plus and multiplication, and that is usually enough to define the size of the memory, because usually you have the size of the element, you have amount of elements, you multiply them together. Maybe if you have a structure, it's going to be a sum of its fields. So you usually need plus and multiplication to actually define the size of the chunk of the memory, right? So, and to not overcomplicate myself the job, also re-implementing this entire thing in Porth, this is going to be like a very small subset, like a few operations and integers. So that's going to be the idea. All right, so porth.py. So unsupported word in unsupported word in what? In memory definition. In memory definition. There we go. So what else do we have in here? So if we encounter keyword, we handle that. Integer, that's fine. Word, that's fine. And here we have essentially unsupported token, right? So, and in all of these to-dos, we'll have to properly report this situation with location and stuff like that. I just don't want to spend time on that, so I'm going to just do it like that. Unsupported token in memory definition, right? There we go. Okay, cool. So this entire thing just evaluates a very small subset of Porth. This is basically a very small subset of Porth. It's 22 lines. It's pretty straightforward. It's pretty simple. Okay, so let's just try to run that, and we don't have a push in here, so this is append. Right. So we'll have to do that as well. There we go. Okay, so we have something not implemented. Cool. Now, what we have to do? We expect only one single number, right? If the evaluation of the expression leaves no integer, or it leaves like 2 integers, it doesn't make any sense. We have to enforce the user to actually provide 1 integer, right? So if you try to do something like 2, 2, right, that doesn't make any sense, right? You have to sum them up. So we need to check that. If stack is not equal to 1, assert false to do, memory definition expects only 1 integer, right? Integer, there we go. So if I try to do that, as you can see, it fails. Memory definition expects only 1 integer, and this is because we have 2 of them. So we're gonna sum them up, and there we go. We're left with not implemented. So this one is gonna be memory size stack pop. Okay, so now we have a memory name and we have a memory size. So what we need to do, we need to probably save. We need to associate memory name with its position, with its pointer, right? So that's basically what we need to do in here. So we also need to keep track how much memory was allocated already, right? So every time you define a block, we basically add that block to the whole memory, right? We add that block to the whole memory. So let's actually keep track of the memory capacity, right? So this is going to be an integer, and the initial memory capacity is going to be 0, right? And every time we allocate like a block of static memory, we're going to add that memory in there. So not implemented. All right. So how we're going to do that? So we have a dictionary of memories, right? And we're going to associate memory name with an address. What's the current address of that specific memory? Well, so if the capacity is 0, we're going to start at 0. So that means, like, yeah, memory capacity is basically the current address of that specific memory. And after we save that address, we can add the memory size of that thing to the final memory capacity. There we go. So that's basically the definition of this entire thing. Yes, right. So there we go. So we have a table that that keeps track, basically the association between the name of the chunk of the memory and its address, and we also keep track of the capacity. So now what we have to do, every time you refer in a code to the name of the memory, we have to push the pointer to that memory, and also we need to pass the capacity of the memory to the compilation so it can allocate that memory in the BSS section, right? So now we have to do something with this kind of stuff, right? All right, so if I try to compile, as you can see, everything compiles, but it's not gonna work, right? So if I take a look at the test.porth, right, so we just allocated the memory, and I don't think it's gonna work. Let's actually try to allocate more chunks of memory, like this. Yeah, everything is working. And in here, if I try to now like use all of that, it is going to fail. Yeah, as you can see, unknown word hello. Even though we defined memory hello, if you try to use that word in here, it will say that it's unknown word, right? And this is because we don't really know what to do when we encounter that word. I think it's handled in the parsing somewhere. Right. Yeah, there we go. So if you encounter a word, we check if the word is part of the intrinsic, so in that case we push an intrinsic. If the word is part of the macros, we expand the macros. Otherwise, we throw an error saying unknown word. So I suppose now we need to check if the word is part of the memories, right? We need to push the pointer to that memory. Right, so we have to do something like maybe program append op type intrinsic. So this is going to be intrinsic. It's allocated in that specific token, and the operand is going to be. So what's the intrinsic? So the specific intrinsic is probably going to be. Oh, it's not an intrinsic, it's actually going to be push int, right? We want to push an integer, basically the pointer. And what we're going to push is the memory. Oh, but memories store the offset from the beginning of the memory. But at this point, we don't know the absolute value of the memory. We just don't know, Pepe laugh. We don't know the absolute value of the memory, we only know the offset from the beginning of it. So that's a problem. I suppose we'll need to introduce a new type of operation to intermediate representation, right? So we already have push integer, we already have push string, and so on and so forth. I think we need to introduce something like push pointer. You know what I'm talking about? Or maybe push memory. Yeah, I think we need to introduce push memory, which will store as an operand the offset from the beginning of the memory, and then the code generation step is going to resolve that offset. Does that make sense? So I think this is how it's going to go, right? So this is going to be the operation, and the operand is going to be memories token value, like so, and then we're going to increment the IP address, right? So we'll need to introduce a new operation into the intermediate representation. Will you have a runtime out of bounds check for named memory addresses? We'll see. I'll need to implement them at least for now, and then we'll see what's needed and what's not. The language is not finished yet. We're in the process of experimenting and exploring the design space of the language. That's what we're doing. So, all right, let me try to recompile all of that. And it says that it doesn't know anything about push mem. So let's take a look at OP type. So in here we have a couple of like operations within the intermediate representation. So let's introduce mem, and that will fail the compilation in all sorts of places, right? So type checking. Type checking is interesting. So as soon as you introduce like a new operation for intermediate representation, you have to go through type checking phase, parsing phase, compilation phase, code generation, simulation, and just add that operation in there. And we have a bunch of asserts that ensure that you go and visit all of those places. All right, so now we're doing a type checking. All right, if you want to type check the OP type push mem, right? So I suppose push mem is simply going to push a pointer onto the stack, right? So there we go. Data type ptr op token, and then it's going to be ctx ip +1. Right, so then I'm going to just increment this thing. Okay, let's go to the next one. So here we have a compilation. Would you look at that? This one is rather interesting, so I'm going to increment this thing, and what we're going to have in here, elif op type push mem. Okay, so I would say that I would expect the operand in here to be memory address, right? I want this thing to be memory address. If it's not a memory address, it's a bug in the parsing step. What we're gonna do in here, 1, 2, 3, 4, push mem, and essentially, the first thing I probably want to do, so we need to move the value of the beginning of the memory to the rack register, right? So we need to do something like move racks, and let's just use the mem, right? So we already have a memory allocated for this kind of stuff, so we'll just use mem. Right, there we go. So after that, I want to add the offset to that register. So the offset is going to be OP operand. There we go. We added the offset. And after that, I'm going to just push that value onto the stack. And there we go. We have an absolute address to that chunk of memory. There we go. I guess push mem implementation would be just redefinition of old mem intrinsic, and you will be able to remove the mem intrinsic as it's now a deprecated macro. Yes, exactly. So that's pretty much the plan. But we're still going to have it in a deprecated section of the standard library. So we're going to just pre-allocate, 640 kilobytes and call that 640 kilobytes mem for the code that already depends on that feature. So you see, we slowly transition to the new way of managing the memory, right? Slowly but steadily. All right, so I think I forgot to put a new line in here. So there we go. And something exited abnormally. So, oh, it already tried to run this entire thing. So yeah, there we go. So it compiles at least, right, but it doesn't run it properly. And the reason why it doesn't run it properly, I wonder. Well, I think it should, right, because we already have a little bit of memory allocated in there. So it's kind of strange that it just didn't work, but it really didn't work. So that is kind of sus. That is in fact kind of sus. So let me see. Let me take a look at the test Porth. Maybe there is something wrong in there. So we increment. We can try to simulate this thing just to see what's going on, right? So let's try to simulate, right? And in a simulation, we'll have a bunch of problems in here. So here's the simulation. So this is going to be the one. Exhaustive OP handling. All right. If OP type. OP type push mem, right? So this is going to be push mem. Does the test include stdlib? Does it need to include stdlib? It does include stdlib. So no, I didn't. Wait, that's a good point. No, we don't have a memory in here. Yeah, so we don't. Yeah, that's a good point actually. That's a very good point. Oh, I see what's going on. The memory size have to be 8. Yeah, the memory size have to be 8. Thank you so much, everyone. So that's basically the problem, I think. Not 100% sure, but I mean, yeah, there we go. It works already. Cool. So it's strange that it didn't work, but I mean, yeah, it works. So we can allocate these chunks of memory and shit and just like, yeah. So what's interesting is that if you try to allocate more than 640 kilobytes, this entire thing breaks. So we have to pass the memory capacity to the code generator, right? So so generate this thing, and we need to know the memory capacity. So the memory capacity is kind of associated with the program that we managed to parse, right? If you do something like parse program from tokens, it returns the program. So along with the program, we need to return the memory capacity, so it knows how much we need to allocate. But the problem is that the program is a list of operations, right? So we need to extend the program. Let's actually make the program a data class that stores like operations, right? And it's going to be data class, and also it's going to have a memory capacity, right? So it's going to be memory capacity integer, and there we go. So the program now is going to be a list of operations plus its memory capacity. And in the future, maybe we're going to have more parameters in here. Who knows? So yeah, that's pretty cool. Everything is going really well so far. And I think this is actually pretty dramatic change, I would say, because we use this type pretty much everywhere, and now where we use this thing, it will break, right, instantly. So let's use a little bit of a compiler-assisted refactoring and just do mypy, porth.py. Okay, so let's see. In how many places this shit broke? Not that many, actually. I expected more. Okay, so here you're trying to do program. You're trying to find the length of the program. In reality, what you have to do, you have to find the length of the program ops. To be fair, like every time you do len program, you probably want to do len program ops. Maybe I can actually replace that like everywhere in the entire code base, and I think that's going to be fine. All right, so value program. Every time we do that, right, so let's actually replace it like so. This is going to be ops. There we go. Anything else? All right, so this is another candidate that may require this kind of treatment. There we go. Anything else? Okay, so oh, program. Oh, because this thing is a list because we are in a parsing. Yeah, in a parsing we define program like list. I should have actually defined it like program. Oh my god. Okay, so I should have defined it like a program. And in here, program is going to be something like this. Operations is empty and memory capacity. Initial memory capacity is going to be 0. So maybe it doesn't make any sense to actually keep track of this thing because we already have a variable of memory capacity inside of the program. So basically we move that variable inside of the program. All right, so let's take a look at the other places where this thing fails. So program append. Okay, so every time we encounter program append, we probably mean program ops append. Let's replace that stuff everywhere. Anything else? Okay, so this is another thing that we want to do. So maybe I could have actually do something more cool. Let's query replace by a pattern. Right, so what if we just take something like this, right, and just replace it with program.ops like this, right? So I think we should be able to do that. So query replace by a regular expression. And replace this thing with that. Is it gonna work? Okay, seems to be working. Seems to be working. Okay, so is it gonna work? Almost working. Okay, so program is not indicible. Where? Oh, it's interesting that it didn't really work for like everything. So if they are on the same line, it just like kind of didn't work. Which is fine, I guess. Stack is already defined. Oh shit. So we have to... Where stack is already defined? So it's already defined on line 1546. And it's a list of operations. Fuck. Okay. Let me see. So maybe we should call this stack something else. How should we call it? Mem size stack, right? So maybe I'm gonna actually select this entire thing and it's gonna be stack mem size stack, and let's replace this entire stuff now. Anything else? Anything else? Is it fine? Stack has incompatible union int. Oh yeah. Essentially, stack expects integer, but the token value might be either integer, string, or keyword. Okay, so we have to make sure, right, so we have to assert that this thing is an instance of an integer, right? So otherwise, the like mypy is not going to let us do all of that stuff. So memory capacity is going to be program memory capacity, and we increment the program memory capacity. There we go. Everything is working now. How about that? So you see how easy it is to refactor huge code base when you have a static typing, right? I cannot believe that some people still defend dynamic typing. Well, to be fair, maybe in 2021, you know, defending dynamic typing is not as cool as it was like 5 years ago. I think people finally start to realize that it's kind of meh, especially for big programs. Otherwise, we wouldn't have such things as TypeScript and MyPy. So yeah, even JavaScript and Python, JavaScript developers and Python developers starting to realize that the static typing is the way to go. So I don't think it's that much of a controversial opinion anymore. Finally, we reinvented the technology from 70s, from 1970. Oh, Clojure developers still believe that dynamic typing is okay. Okay, sure. Abusing duck typing is sometimes fun, although evil. In my opinion, like, people use dynamic typing and duck typing interchangeably, but in my opinion, dynamic typing and duck typing as like orthogonal things. Right. So basically, this is how I define those things. Dynamic typing is when the types of the values are checked at runtime. That's what I mean when I say dynamic typing. Duck typing, on the other hand, is the type system where if something behaves like a duck and quacks like a duck, that means it's a duck, and that's why it's called duck typing. So essentially, if you have a program, a function that accepts a duck, right, and you say duck quack, right? So you don't care whether quack is a class of foo that has a method quack or bar that has a method quack. You don't care, right? Because both of them has a method quack, so it will work with this function. But it doesn't prevent you from checking this kind of stuff at compile time. In fact, you can quite easily imagine a language where, this kind of stuff will be checked at compile time. So the compiler will just see, okay, what instance of a class you put into this function? Okay, it's a foo. Does it have quack that this function expects? Yes, it does. So if it doesn't, it will fail at compile time. So it doesn't necessarily have to be checked at runtime. It could be also checked at compile time. And as a matter of fact, I think a good example would be like a Go interfaces. Aren't Go interfaces basically that? Essentially, you describe what you expect, what kind of methods you expect from the type, and then if you have those methods, it will pass, right? So it's kind of a form of duck typing in that definition. So I personally don't really understand why people use duck typing and dynamic typing in like synonyms. For me, these are different things. They're orthogonal. You can have dynamic typing in statically typed language. You can have dynamic typing in dynamically typed language. Right. So you see what I mean? But maybe I'm wrong. But this is basically what I mean when I say those things. But maybe I'm misunderstanding something. It's just like my point of view. I don't know. All right. So let's continue. C++ templates are a good example of duck typing at compile time. Yeah, I do agree with that, actually. They're a pretty good example of that. Right. What do we have? What I was doing? Okay, so we checked everything, and now I want to try to compile my test program. Okay, everything seems to be working, and if I try to run this entire stuff, it works, which is kind of sus. Why was it so easy? Like, I just followed the process of, basically changing the compiler until my program compiles, and now I have a feature. What the fuck? Oh, by the way, now we have a zero cost abstractions. Now, if you don't allocate any memory, it's not going to be put into the final executable, right? So if you have a hello world, right? So hello world, let's actually put Porth, and let's maybe include std.porth, and this is going to be hello world. New puts, and I'm gonna try to compile the hello, right, and I'm gonna try to run it. If we take a look at the hello assembly, oh fuck, it still allocated this thing. Yeah, okay, so I'm really glad that, you know, I decided to take a look at the assembly because it reminded me what I forgot to change. Right, so essentially, we don't need this global constant anymore. Right, we don't need this global constant. So I'm gonna remove this global constant and I'm gonna try to type check this thing one more time. Right, there we go. So mem capacity, right, so now we have to take the memory capacity from the program, right, that we calculated during the parsing, right. There we go. So memory, so it's called memory capacity, sure. So, and another memory capacity comes in here, so it's going to be program memory capacity. Okay. There we go, cool. So if I try to compile the hello world now, and I take a look at the assembly, there we go! We have 0. Isn't that cool? I think it's pretty cool. We still have a little bit of a memory in the data section for the strings, but for BSS, since we don't use any memory, we just don't have anything in here, right? So that's pretty cool. We can try to allocate something, right? So I'm gonna go to hello, right? So let's actually go and just compile the test Porth, and let's take a look at test awesome and see how much we have in here. So we allocated 280 bytes, right? So, and that's how much memory we were gonna use at runtime. So as far as I know, like since BSS is not initialized section, right? So I would presume that it's not actually stored in the executable. So I would assume that the only thing that is stored in the executable is the size of that section, and that basically tells the operating system like how much it needs to allocate for the program, right? So yeah, so it's gonna allocate 280 bytes and stuff like that. BSS is not stored, yeah, exactly. So that's what I would assume, because it doesn't make sense. So data, on the other hand, is probably stored, but you need to store it because it's initialized data. All right, so what we want to do now, we probably want to go ahead and finally remove the mem intrinsic. Yes, let's go ahead and remove the mem intrinsic. So, okay, finally, we don't have a mem. Okay, I'm going to try to compile this entire thing, and we have a couple of places. Right, so you see, these asserts are useful not only when you add new intrinsics, but also when you remove them, because you need to not forget to remove them from all of these places where you use them. There we go. So here's another one. So mem, it's gone. Another one. 42 mem. It's gone. Everything seems to be okay. So I think I forgot to test the simulation of our nation. Oh shit. Something is wrong. I won't believe that the simulation takes this much time. So there's something wrong. There's 100% something wrong. Okay, so in a simulation, simulate. So maybe it's something with the pointer when you push. Oh. Okay, so this does not produce any runtime error. First of all, this didn't produce any runtime error because this entire thing was interpreted as true. Furthermore, this entire shit was not caught by MyPy. Right? Do I understand correctly that MyPy is not going to complain about this thing? Well, at least like it complains about other things, right? Yeah, it's not going to complain. So neither Python runtime nor MyPy static checks will help you in this kind of situation. But Zozin, Python is designed to be easy to program in. Oh, it's all about productivity of the developer. Oh. Anyway, so simulation. Okay, so this is gonna be the instance. All right. This one has to be +1, and when we push mem, I have to do something like assert is instance op operand, right? Op operand. So what's that? Mem address, right? So this is a mem address. This could be a bug in the parsing step. It's time to write our own language. Oh wait, that's exactly what we're doing. That's precisely what we're doing. So the question is, what's the offset of the memory? So the memory is probably located somewhere. Oh yeah, so this is a memory buffer pointer. So let me find the mem. So what we were doing here, we're actually pushing mem buff pointer, so I might as well do it like this, right? So that's what I push in here, right? And what I want to add is op operand, because that's basically the offset. Okay, so that looks okay. Now, if I try to simulate this entire thing, Python exception during simulation expanded from this thing. Okay, so that's cool. Oh yeah, I have a pretty cool feature that if you have an exception, Python exception during simulation, it also tells you where exactly during simulation it happened, right? So during interpreting Mem Copy, you had a Python exception, and it actually tells you all of these locations in here, and then you can find where in Python code it also fails. So basically, I wrapped this kind of stuff in a huge try catch, and every time it catches the exception, it tells you like as much information as possible that happened during the simulation. That's actually pretty cool, I think. I don't know. Okay, so here I forgot to decrease the amount of this thing. All right, so as you can see, simulation says hello world, compilation says hello world, everyone is happy. Isn't that cool? Isn't that cool? Oh, I think it's pretty fucking cool. Cheers, by the way. So, so maybe we should create like a separate branch. Better memory. There we go. So what we want to try to do now, I think, we need to try to run the tests and see how miserably they fail, right? So I'm going to try to run the tests. And as you can see, they're starting to fail at some point, right? So, and what they say is we have a known word mem, right? Because we don't have mem anymore, we have a completely different way of managing the memory. And this is where the deprecation policy comes in, right? So what we're gonna do now, we're gonna allocate mem of 640 kilobytes. There we go. So now, this is gonna be used by the legacy code, right? This is going to be used by the legacy code. The unit tests are passing, right? So the old code does not distinguish mem as an intrinsic and mem as the named region. So yeah, that's pretty cool. So if I know that a few people out there actually actively writing programs in Porth. Even though I said, please be careful, right? So this language is a work in progress and anything can change at any moment without any notice. So use this language at your own risk. Some people, they don't care. They just program in that language and they have fun. And there's nothing I can do about that. So yeah, if you like to have fun, just have fun. So, and for those people, I'm trying to sort of follow the deprecation policy. So if you do things in this language, I'm going to try to maintain as much of the backward compatibility as possible, but if I'll have to break something, I will break it, right? So yeah, so I have an opportunity to actually preserve backward compatibility with the old way of managing the memory. So if I have an opportunity, I'm going to just use it. Right, so, and then eventually people will be able to slowly transition to a different way of managing the memory. All right, so all the unit tests are passing. So let's take a look at the examples, right? Because we have other things, right? So are examples passing as well? So we have rule 110, which is pretty slow, but seems fine. And now the slow Euler problem solutions. They're so slow we have to use PyPy to even run them. So yeah. I suppose the fourth problem actually like goes for solid 1 minute when I'm streaming with OBS, right? So we'll see how it goes. And the reason why they're so slow is because Python is a very fast language and I'm using a wrong data structure. Right, that's the reason. That's precisely the reason. Okay, everything seems to be okay. So let's do a committee and maybe even a pushy. All right. Oh, by the way, I forgot to do a very important thing. Can we compile Porth with the new mechanism? So we're gonna have Porth. Okay, so I suppose I have to do just com. Okay, so we managed to compile Porth with porth.py. By the way, so Porth is relatively big already. It's like half of the thousands of lines of code, right? So we have a lot of things in here. And do you want to see the assembly that is generated from Porth? Do you want to see the assembly? The assembly is actually quite scary. First of all, at the bottom, you have shit ton of strings. Right, so here are all of the strings that we use inside of the Porth compile. Right. On top of that, in terms of the amount of operations, there is 11,000 of operations. Right. And this is because of all of these macros expansions that we have in there. So it's quite beefy. And furthermore, the final executable in here is 0.5 MB. Right. So there's a lot of crap in there. So far, Porth supports push int plus minus print dupe drop. And that's it. So I think I can add support for the rest of the intrinsics because intrinsics specifically are just basically copy-pasting implementation from Python. Control flow, like ifs and whiles will be a little bit involved, but intrinsics should be actually pretty straightforward. We can actually test some stuff. So for instance, full Porth. For instance, here you can just have something like, oh my god. 0, right? You can duplicate this thing, print it, increment by 1, and just do that a couple of times, right? And then you can drop this entire thing. So then you can use the Python simulation, and you can just run this entire thing, and as you can see, it prints these things. And then you can use the Porth written in Porth, and it works, right? So this is a program that is simulated by Porth interpreter written in Porth. Isn't that cool? I think it's pretty cool. So, and we can compare, now we can compare the simulation speed, right? So the simulation of the Porth written in Python is 125 milliseconds, right? 125 milliseconds. The simulation of Porth written in Porth is 1-2 milliseconds. But obviously Python implementation is going to be slower because of all of the convenience for the developer that the developers of Python crammed into the language. Obviously, right? Look at all of the convenience. Look at all of the convenience for the developers. Like, that's a fat convenience. Holy fucking shit. All of that convenience just justified like 100 times. Just like, oh my god, that's a fat, juicy convenience. Anyways, so what I was doing. Oh yeah, I want you to actually maybe commit everything. I want you to commit everything. So there we go. 100x more productive, yes. 100x more productive. Okay. Fix typo. Fix mistake, maybe error in the documentation. And implement memory region definition, right? Memory region definition. I'm gonna push that right into the repo. So let's see if this feature actually improves the quality of our life. Okay, so here's the memory layout. I want to be able to allocate memory layout without all of this bullshit, right? I want to just be able to say memory. God damn it! I probably need to go to the editor folder. Right, I'm gonna go to the editor folder and I'm gonna go to Emacs local. Right, I'm gonna copy the Porth mode in here. Right, so the Porth mode, does it have a memory? Yeah, it does have a memory. So let's restart Emacs, because Emacs is an operating system. So every time you change something, you have to reboot your operating system. Right, so. So now, so this is going to be Porth. So here's the memory, and there we go. So I'm gonna actually say put D buffer capacity. Right, so now I can just directly say, okay, I want a memory region that is called put D buffer, and it has the size of put D buffer capacity. That's what I want to have, without any of this, like, let's take the previous variable and just add the size. And no. Just let me give it a name and the size. That's what I wanted the whole time. All right, so let's try to compile this entire thing, and I think it will fail because we didn't implement one important feature for the memory definition. So let's try to compile this entire thing. So it's going to be Porth, and there we go. So we have an unsupported word in the memory definition. Right, so this is what we hit. Essentially, inside of the memory definition, we allow AND keyword, integers, and plus and multiplication. But something like this thing is neither of those. So we need to perform a macro expansion, right? So essentially, when we encounter an unknown word, we need to check if that unknown word is a macro, and we need to perform the macro expansion for that word. Right, so, and that will allow us to use the macro things within the memory definitions. So let's go ahead and do that. Right, so if token value is in macros, if it is in macros, we have to perform the memory definition. Okay, so this is going to be something like false, not implemented, macro expansion, expansion in memory definition. So let's actually confirm that that's exactly what's going on here. Yeah, it is in fact what's going on. Macro expansion. And how do we expand the macros? So if I remember correctly, you encounter a word, you confirm that this word is in macros, you also check the expansion limit and stuff like that, and you just expand the macro and add the expanded tokens into the token stream. Right, and that's precisely what we can do in here. I think we can just copy paste this chunk of code in here. You see, implementing compiler is easy, you just copy paste stuff from like around surrounding code. And there we go. Okay, so it compiles now. Cool. No complaints and stuff like that. So let's actually go ahead through all of these variables and maybe like rewrite them into memory regions. I think that will be actually kind of like super useful. So memory, file path sister. File path sister is a pointer as far as I know, right? So maybe we're gonna have something like size of PTR. By the way, in the standard library, I defined a couple of things like size of U64, size of U32, and maybe I'm gonna also define something like macro size of PTR, right? So it's gonna be like U64 for now. Okay, so Porth. So FD, right? So we have FD now. FD, as far as I know, is U64, right? So we're gonna do something like size of U64. You know, I really like these constants that I defined. They almost make it look like a variable definition. So you have a variable with the name, and here is the type of the variable. So basically, so we have some sort of a memory definition. We don't have like a type checking for those things yet, but maybe in the future we're gonna have something like that. Right, so maybe at some point we're gonna have something like variable, and then you would define a type, right? And that will act like a pointer to memory of that specific size and that specific type. Maybe in the future we're gonna even have like a, you know, structure definitions like struct, string, and you will define something like count, U64, data, pointer, right? And then you'll be able to define something like file name of that thing. And yeah, all of that stuff is going to be like basically variants of that, but type checked. But we're going to implement all of that a little bit later. Okay, so stat buffer as far as you know is size of stat, right? So this is the size of stat. So content, if I remember correctly, is a size of string. So this is a string. This is a memory. So I just want to define all of these things and see if the compiler still works. Okay, line is also a string. Word is also a string. So we're gonna align everything in a pretty way. What does memory do? It basically reserves a chunk of memory of this size in the BSS section, and then you can refer to that chunk of memory through this name. If you basically use this name, it will push the pointer to that chunk of memory onto the stack, so you can read from it or write into it. So we have named chunks of memory. So yep. So that way we sort of define the variables. Right? Line number, as far as I know, line number is going to be essentially U64. Right? So this is a U64. Line start, if I remember correctly, it's a pointer. So this is going to be the size of PTR. str equal. Okay, this one is interesting. So this stuff is needed for str equal. So maybe I'm going to actually keep that thing in here. So this is going to be memory. So, and here, what do I keep? What do I keep? I think it's going to be size of str, maybe strb, yeah, like this. So these are sort of like a local variables for this specific macro. Do we have anything else? Okay. Stack count, this one is going to be size of U64. Simulation stack, oh, okay, so this one is very interesting. So simulation stack, the element of the simulation stack, is size of U64, and then we have to multiply it by the simulation stack capacity, and the simulation stack capacity is this thing. Okay, so now we need to define the ops, and we need to have something like size of ops, ops capacity multiplied. There we go. So all of that has to be memory. Okay, finally. Hopefully we're done with this tedious work, but this is a tedious work that has to be done. It just has to be done by somebody. There we go. So we will also align maybe ends, right? Query replace. Actually, align rejects, and there we go. So does it look cool? Does it look cool? I think it looks pretty cool. So this is basically the memory, the global memory variables and stuff like that. So that's pretty cool. So we got a sub from BuyerBroTV.
Hello, Epic Port Developers Cedinko.
Hello, BuyerBroTV. Thank you so much for 5 months of Tier 1 subscription. Thank you, thank you, thank you. And welcome back to our Epic Porth Club. Cheers. That one's for you. Always glad to see you, buddy. Okay, so let's try to compile this entire thing. And we have unsupported word in memory definition. And the question is, what is the unsupported word? Maybe for the time being, I'm going to actually print that word in here. So this is gonna be token value. Don't Pew, thank you so much for Twitch Prime subscription. Thank you. Your first subscription, by the way, and welcome to our epic Porth Club. Isn't that cool? Be a proud member of the Porth Club. Porth? Oh, by the way, I think Stevenson suggested like a pretty cool logo for Porth. Basically a seal. Chiroptical, thank you so much for 28 months of tier 1 subscription. Thank you. Porth. So this is actually perfect. I would never think about that. Just a second. I put it in the drawings in our Discord server. Thank you so much for the subscription. Thank you. Yeah, Stafson. Yeah, Stafson. I hope I pronounce their name correctly. So Yesu. Just a second. So this is the logo. I'm actually considering to use it as the official logo of Porth. I'm gonna put it in the chat, and for anyone who's interested, I'm gonna put it in the description, like this. Suggested Porth logo. I think it's kind of cool. I especially like a hand drawn like a vibe of it. Mkalo, thank you so much for gifting tier 1 sub to Janix69, and Janix69, welcome to our epic Porth Club. It's actually so cute, look at that, it's so cute, I love it. You know what it's missing? It's missing the shines in the eyes, I think, kind of. Let me actually see if we can fix that. Right, so let me download this thing. PNG, and can I open it with my paint or something like that? It stares right into your soul. Yes, that's precisely what it does. So I think what it's missing, in my humble opinion, is something like this. Now it's way cuter. What do you guys think? I think it's pretty cool. And also maybe you can do something like that for the nose. I mean, of course. So some little bit of a highlight. So yeah, I'll think about that. So thank you so much for suggesting the logo. I still haven't decided yet, so it's just like, yeah, in the process of deciding what's gonna be the logo of Porth. But I really like that. Let me see. So I wanted to print the size of ops. Okay, so we don't have a size of ops yet. Let me go ahead and introduce that. Porth. Oh, it's not ops. Yeah, it's a single op. So ops cap. Okay, so that makes sense as well. Ops cap. So where are we going to define all that? So ops cap. How many operations? What's going to be the capacity? Let's actually define 24, right? And that should work, as far as I know. Push OP. So since we're starting to have the capacity for the operations, I think we need to check for the capacity. Assert ops cap, but I'm not going to do it right now, right? So we're going to do that a little bit later. Okay, cool. So now let me check if Porth still works. Seems to be working. Can I simulate like a simple test thingy? Okay, so I cannot simulate because it doesn't know anything about include. So by the way, Porth reports the locations of the tokens. Right, this program that reported this error is written in Porth. Yeah, it is written in Porth. Okay, so what was the other program? Yeah, there we go. So everything seems working, right? Everything still works. So that's pretty cool. So we're already officially using the new mechanism of memory management in the compiler, and that finally allows us to take put D and move it into the standard library, because now standard library has a way to just reserve a little bit of memory for itself, right? So yeah, the standard library can just say, okay, give me this amount of like memory and I'm gonna use it for myself. And there's no need to, like, for different parts of the program to communicate who allocated what and whatever. So yeah, they just reserve like specific sections of the memory. So let's go ahead and move put D into the standard library, right? So where are we going to put that? So I'm going to put it somewhere here. So this is a put D, and of course the put D buffer capacity is going to be also defined in here somewhere, right? Put D, and the macro put D is going to be allocated in here. There we go. So that's what we have in here. Yesu. Kawaii freaking desu. str equal, by the way, now can be also moved into the standard library, of course. So we have str, I don't know, like str trim, str chop, and some other stuff. So our standard library is actually growing in terms of like supported operations. We have like comparison of the strings. You can like chop the strings and some other stuff. Here's the string definitions and whatnot. So it's pretty cool. It's pretty cool. All right. So can we now recompile the entire thing? So we're gonna just try to recompile Porth. And everything seems to be working. Everything seems to be working. So what do we have in here? Okay, so we fixed that. So let's do a committee for this entire thing. Use memory sections in Porth. There we go. So one of the things I probably want to do now is just run the tests and see if they fail anywhere. Okay, so now let's try to run the example. Hopefully nothing breaks in here. Okay, something breaks. Oh yeah, because we have a redefinition of put D, because I had to copy put D in every program that I used. I couldn't move it into the standard library, but now I can just do that. There we go. Oh shit. That invalidates like this entire memory layout thingy. Fuck. Well, okay, so that means I'll have to just go ahead and, you know, refactor all of this entire thing into the memory sections. So this is going to be macro. Delta time plus 16. Why is it 16? What delta time is used? What is it? Ah, I know what it is. It's the time definition by nano clock or something. Nano. If you take a look at the clock nano sleep, all right. Clock nano sleep. That's a syscall. It accepts time spec, right? So, and time spec is a structure that consists of two, you know, 64-bit numbers, right? So yeah, that's basically what it is. That's why delta time is actually 16. So, and in fact, maybe I can define something like macro size of time spec, and I'm gonna say that it's a 16, right? So here we go. Delta time is going to be size of time spec. Board index is probably U64, size of U64. Neighbors. Neighbors is just a counter, right? So it's going to be size U64. Value, I don't remember what it is, but it's just like one of those things. Board base, I presume it's a pointer, right? It's some sort of a pointer. Ooh, yeah. So essentially, it's a board size. Right, it's a board size, but multiplied by 2, because there's 2 of them. Okay, that makes sense. And display is essentially, I suppose it's just a row, but I'm not sure. I think it's some sort of display a row, and we're probably displaying everything by a single row, so it's supposed to be something like rows, but plus 1. Yeah, and this entire thing will just become a memory. There we go. So this is just a memory. Delta time, size of U64, board base. So board size that thing, and display, it's a display row, because we Save this entire thing into a row. Actually, this is calls, right? So this is called because that's the size of the row. Okay, I'm starting to remember this entire thing. Okay, cool. Is that Polish notation? Yes. Mem2pl can confirm. I'm sorry. All right, so let me try to actually compile this entire thing. So this is going to be com example goal, and everything seems to be compiling. So, and let's see if goal is not broken. We need a parenthesis over here, yeah. Yep, still works. Didn't break anything. This is kind of sus. Why is it so... Why does it work first try? Well, actually, I bought a new tea today. New Earl Grey. Maybe that's the reason? Maybe that's because of the tea? Okay. So let me see. Okay. To fix compilation of goal example. And now let's actually test the Euler programs. Euler, py. Okay, problem 7. Have you checked the number of operands in the memory parser? What happens with plus? I think, yeah, I see what you mean. So what will happen if you, do something like memory var 2 plus end? So I suppose it will throw a Python exception. That's a good point, actually. Thank you so much. So nothing bad is going to happen, but nothing good either. So memory var 2 plus, right? So Porth by compile. What is it called? Hello.porth. Yeah, there we go. It just throws a Python exception, which is definitely not ideal. Right, thank you so much. So I'm gonna put it to do in here because it's not like critical, but it would be nice if you know, if it at least told the user that, bruh, you're doing something fishy in here. Check for stack underflows in memory definition. Right, so that's a good point. Alrighty. Okay, to do, I don't know what to put in here, just editing new to do. Cool. So now we have a way better way of managing the variables and stuff like that. That's super cool. Really like that. I really like that. Does anyone have any question about what just happened? Can functions have local stack memory like an strlen? I think they can, kind of. We can kind of emulate that now, in some sense. It's not ideal, but it's something at least. Str equal, where is my str equal? So essentially, if your function needs, you know, some sort of local variables, you can just allocate them and prefix them to indicate that only that function macro is allowed to use them, and you can just like use it like so. Since you can define arbitrary like sections of memory, it works, right? You don't have to communicate between different parts of the program and stuff like that. What I'm thinking is that we can introduce some sort of like a you know, memory arena of a particular size in the standard library, and a bunch of things that allow you to allocate a little bit of memory within that arena. And maybe this is going to be the arena that is going to be used by all of the programs in the standard library to allocate local variables. So we can try to do something like this. But on top of that, you can define any like regions of memory, but maybe there should be some sort of a standard. I don't know, I haven't decided yet. So this is basically the new possibilities that we can have. Right, we're still exploring the space of possibilities of this language, right? Yeah, like a temporary allocator, right? So we'll see. But for now, you can just define arbitrary sections of memory and just use them for something. Okay, so does anyone have any questions? The local libraries should be allocated on stack. There is already push and pop. Should be? I don't think there should be. And what is a stack? What is a stack? Because I can just allocate some memory in here and say that this is a stack. There we go. Thread local stack. Okay, so create a stack for each individual thread. Right. Thread 1, thread 2, thread 3. And use those stacks only in those threads, and don't use these stacks between the threads. You can even maybe allocate the thread local stacks in dynamic memory, why not? Through a map. So I didn't see any problems, I didn't see any contradiction here. It's amazing how seeing this from the ground up solidifies all the ideas I already have. Everything seems much simpler. Exactly, because we got rid of the unnecessary details. Right, it's really difficult to see what's going on when you have like a pile of abstractions. Right, abstractions. Right, when you get rid of all of that, it becomes actually much simpler and much clearer. You can build your own abstractions on top of that. So everyone knows how to build more and more abstractions, but not everybody knows how to tear down the abstractions. I think tearing down the abstractions is the skill that is going to be useful in the next like 10 years, when the software systems will become so complicated that one of the ways to improve things is going to be tearing down the crap that we piled on top of it. So, yep. It's a very important and useful skill. What made you decide to make this language? Boredom. That's what made me make this language. I think I found a bug. Putting a memory block in a macro crashes while parsing. Oh, that's actually very interesting. So, pop from empty list. Okay, so let's take a look at what's going on. So bug. Porth. Porth. Memory block inside of a macro. Okay, so macro full. Memory bar. 69. Porth. Oh, I know. I didn't even have to look at the code. I already know why it fails. Okay. I forgot about it. This is because we don't have an assert in there. I forgot to add the to-do assert. You know, every time you change the amount of keywords, just go there and don't forget to update something. This is confirmation that those asserts actually work. Okay, let me see. Let me actually confirm that. So it's gonna be bug Porth. There we go. And this is because let me see. Macro. When we are grabbing the body of the macro, we check if one of these things is if, while, or macro, and now we have to add keyword memory. And once we edit this thing, it will not crash. And the reason why I missed that is because I forgot to put my famous, I don't know if it's famous actually, but my favorite assert, right? So basically len keyword, right? And how many keywords do we have? So let me actually do that. Yeah, 9. Right, essentially, if I edit a new keyword, this assert would fail and remind me that I have to add this thing in here. You see? So this is a confirmation that these asserts actually work and like help you to not introduce errors. So that's actually pretty cool. I forgot to put assert in here, and there you go. So I made exactly the bug in here. So exhaustive handling of keywords in parsing macro body or whatever. Right. Okay. Fix bug in while parsing macro containing memory block. There we go, and I'm gonna push that right at the repo. That the sus you have sensed before. Yeah. I assert in every line, same. Does anyone have any other questions? Now having redefinable macros got more useful for only allocate memory once macros. Only allocate memory once, maybe. We'll see. We'll see. I'm not sure if I'm gonna even implement macros in Porth. Because I think the implementation of macros is more complicated than is needed for Porth. I have a feeling when Porth will become self-hosted, it probably won't have macros. I have a couple of ideas on how to make the self-hosting a little bit simpler, but I'm not going to reveal them yet because I'm not 100% sure, right? So I'm using macros like a sledgehammer, or that allows me to explore what kind of features are needed in the language. So essentially, macros are useful because they allow you to emulate a lot of features of the language, right? Because it basically can tuck any sequence of tokens under a single token and sort of write your own DSLs and explore what kind of features you need in the language, like what kind of useful features, right? So the macros helped us recognize that we need memory blocks. Right now we have a memory block thingy. So it will also help us recognize that we need something else. And maybe if we implement all of these features that macros show us we need to implement, maybe we won't need macros anymore, at least for self-hosting. Because I want to achieve self-hosting as easily as possible, right? So I want the language to be as easy to implement as possible, because the language is dumb and I don't want to implement complicated language in a dumb language. So I don't want to write complicated code in a dumb language. That's what I wanted to say, right? It's kind of bad to have a very dumb language that has a complicated implementation. See what I'm talking about? Right? So if the language is dumb, the implementation of that language better be dumb. Right, so then you'll be able to implement this language in itself. But once we achieve the self-hosting and we start to expand, compiler and introduce a lot of quality features, quality of life features, maybe we're gonna bring the macros back and maybe introduce more. I have a lot of ideas for type system, for instance. I have ideas for structures, for instance. I do want to have structures that are part of the type system of Porth and that are properly type checked and stuff like that. So, yeah. And then add the C preprocessor to build process for macros. We're not going to do that. We're probably going to have like a proper meta evaluation, essentially like being able to take Porth program and evaluate it at compile time. Kind of similar to how we do that for the memory definitions, but for the memory definitions, we use a small subset of Porth because I don't want to overcomplicate things. So, yeah. Will Porth support floats? Not until we made it self-hosted. So, I'm pretty sure you don't need floats to make a self-hosted compiler. In fact, people had self-hosted compilers before hardware even supported floating points. Right. So hardware for some time only had integers, right? And we had programming languages working on that hardware and they were self-hosted. So you don't really need floats to make a self-hosted compiler. But after we implemented the compiler in itself, and we'll try to do something more complicated with that compiler, for instance, make a game that renders with OpenGL, we may start introducing floating points, yes. Sure. If you want to do some OpenGL graphics or any GPU graphics, you better support floating points, because all of the GPU graphics, like, it works with floating points, right? You better have that. And we're going to have that. I wrote float addition and multiplication in Porth. Nice. To be fair, how did you do that? Did you introduce new intrinsics? I plan to actually have a type system that will allow me to overload plus minus multiplication for different types. So I want it like to dispatch between different kinds of multiplications at compile time based on the types and stuff like that. Bit shifting. Oh, holy sh! Oh, I thought you hacked the compiler itself. I thought you actually extended the Python script and added. So, okay, you implemented floating point using bit shifts and stuff like that. Holy shit! Oh, great. That's a very dang way of doing that. Oh my god, I love that. It's a very dang. Nice. All right, so I think I gotta go. I already streamed for 2 hours, and I think yeah, today's stream was pretty productive. And yeah, I gotta go. Do you plan on having ASM-like things after achieving self-hosting? I don't want to reveal too much, but goddamn. The short answer is yes. The short answer is yes. The longer answer, I'm planning a pretty cool feature, actually. So look at some of these intrinsics. So if you have something like plus, all right. So you see, these intrinsics, they spit out essentially the assembly code. I want to have a way to do shit like macro dupe, and then say something like NASM, and you literally put NASM in here, like pop or x, pop or bx, and so on and so forth. And then you say compile in NASM mode. And in NASM mode, the compiler will put a header and footer, and it will only execute NASM sections. Right, it will collect NASM section and it will actually implement this thing like that. If you compile it in a different mode, for example, gas mode, it will work with gas blocks and stuff like that. So I don't know exactly how this will work, but we will be able to move this hard-coded string outside of the compiler and put them in the libraries. So you can like be more flexible in terms of what kind of platforms you support. So that's what I'm thinking about. It's not just going to be like ASM things. It's going to be like a core functionality of defining your own intrinsics and stuff like that. But I haven't figured out how exactly it's going to look like. But yeah, so that's what I plan. I actually planned this kind of stuff like since the beginning of the language. I have a couple of other interesting things, but I don't know. I still need to explore this kind of stuff. We'll see. And you can precompile the stdlib for other macros as ASM and just using... Yeah, but we need to explore how to do that and implement all of that. So we'll see. I don't know. Don't want to promise too much because maybe it's not going to be feasible to implement. Who knows? All right. So I guess today was a pretty cool stream, and I gotta go. Thanks everyone who's watching right now. I really appreciate it. Have a good one, and I see you all on the next stream. Check out all of the links in the description if you're watching on YouTube. Check out the source code of the project. Check out the YouTube channel where I upload all of this stuff. And I don't know, let's maybe rate somebody. I don't know. Is anyone streaming on the science? This is not a science and technology. It's a software and game development section of Twitch. Oh, there is a music in here. I forgot about that. Handmade Hero is streaming. So is Casey... Oh, okay, Provad is streaming. So I think we need to rate Provad because he rated us a couple of times and I keep forgetting to rate him. So he's an epic Russian hacker. He's doing like a very advanced computer graphics GPU stuff. He usually streams in Russian, but he speaks English really well. So just go to him and tell him to speak in English, and he will answer all of the questions in English. So I'm gonna just write them. Provod. All right. So get ready for the raid. Get ready for the raid, and I see you all next time. Love you all.